Now we discuss properties of binomial distribution. First of all, suppose x follows binomial distribution with values n and p, where n is the number of trials and p is the probability of success. We have the equation p of x equals ncx p raised to x q raised to n minus x. X values are 0, 1, 2, etc. n, and the probability of success p lies between 0 and 1, and q is equal to 1 minus a. You can see that the variable x in binomial distribution represents number of successes in a set of n trials. It is very much clear that never this number of successes in n trials can take continuous values. So the variable x following binomial distribution is discrete and it has values at 0, 1, etc. n. Maybe no success, 1 success, 2 success, etc. All the trials success, that is n success. So the variable x following binomial distribution takes only discrete values. Now next we consider the mean and variance of the binomial distribution. Mean of the binomial distribution is obtained by the equation of E of x, which is E of x equals sigma x equal to 0 to n x P of x. Now here this P of x has the equation n c x p raised to x and q raised to n minus x. That is summation x equals 0 to n x into n cx p raised to x q raised to n minus x. Now this can be written as x equals 0 to n x into n factorial y x factorial into n minus x factorial p raised to x q raised to n minus x. This is by expressing the combination n cx using factorial term. We have a result NCR equals n factorial by r factorial into n minus r factorial. Now, you can see that the summation is from x from 0 to n, the values of the variable. But when x is 0, the entire summation becomes 0 because 0 into n factorial etc. Therefore, the entire sum will be 0. Therefore, the summation is effectively starting from 1 onwards. So we write it as summation x equals 1 to n. Now, in x we get in x factorial we get terms from 1 to etc. x, and here 1x. So you can cancel this x and the last term of the product in x factorial, that is x. Therefore, it is n factorial by. Now, last but 1 will be x minus 1, x minus 1 factorial, now n minus x factorial, and p raised to x and q raised to n minus x. Now we can rearrange the terms given in the summit by taking one n outside, the n from n factorial. So the terms will be n minus 1 factorial here and one p from p raised to x. Therefore, it becomes np outside the summation and x equals 1 to n. This is now n minus 1 factorial and the denominator will be x minus 1 factorial. Now n minus x factorial p raised to x minus 1 and q raised to n minus x. You can see whether the equation balance, that is n into n minus 1 factorial, the total becomes n factorial, and the p outside and this p raised to x minus 1 together it makes p raised to x, and denominator no change at all. Now p raised to x minus 1 into q raised to n minus x. Now we can close this factorial terms using the same equation of combination 2 factorial, that is it becomes np summation x equals 1 to n Now n minus 1 c x minus 1 p raised to x minus 1 q raised to n minus 6. Now this means that x equals 1 to n minus 1 c x minus 1 p raised to x minus 1 q raised to n minus x is a binomial expansion of q plus p whole raised to n minus 1. It can be verified by considering the values of x from 1, 2, 3, etc. n. That is, if you put x 1, 2, 3, etc. n in the summand, the terms generated will be similar to the terms of the expansion q plus p whole raised to n minus 1. We can list the terms of that q plus p whole raised to n minus 1 and also verify the equation. That is, np into, when you put x equal to 1, it is n minus 1 c0. That is, by putting 1 here, 1 0, p raised to 0, q raised to n minus 1. Next is x equal to 2, then it is n minus 1 c1. Now, p raised to 1, q raised to n minus 2. Now, the third is x equal to 3, it is n minus 1 c2. Now, p square q raised to n minus 3, etc. Finally, when x becomes n, it is n minus 1 c n minus 1. That is, here x equal to n, p raised to n minus 1 and q raised to n minus n, which is 0. So, it becomes np into q raised to n minus 1 plus n minus 1 c1 p q raised to n minus 2 plus n minus 2 c3 p square q raised to n minus 3 plus etc. The last will be, this is 1, this is p raised to n minus 1 and this q raised to 0 is again 1. So these are the terms obtained by putting x 1, 2, 3, etc. n in that summation. You can see that the terms inside the bracket represent the terms of the expansion q plus p whole raised to n minus 1. And this is by binomial expansion. We have seen the binomial expansion a plus b whole raised to n, which is a raised to n plus n c1 a raised to n minus 1 in b plus etc. plus b raised to n. So when you choose a as q and b as p and n as n minus 1, these terms will represent q plus p whole raised to n minus 1. And you can see that q plus p is 1, so it is np. Thus, the mean of binomial distribution is np. To discuss the variance of binomial distribution, we consider the equation of variance given by e of x equals e of x square minus e of x the whole square. Here, the second term e of x already denominated as np, so I have to find out only e of x square. See, e of x square is obtained using the equation e of x into x minus 1 plus x, because here we cannot consider e of x square and sigma x square p of x. That is, e of x square equals actually summation of x equals 0 to n x square p of x, because sigma x equal to 0 to n x square into n cx p raised to x q raised to n minus x. This summation is not factored into a closed form. So we consider a diversion here. The diversion is by taking x square as x into x minus 1 plus x. You can see that this is again x square minus x plus x, which is x square only. So the second moment of binomial distribution is obtained by considering e of x into x minus 1 plus x. Here we consider the first term e of x into x minus 1. This is actually e of x into x minus 1 plus e of x. So the first term is e of x into x minus 1. This is sigma x equal to 0 to n x into x minus 1. Now n cx p raised to x q raised to n minus x by the definition of expectation. Now that is equal to summation x equals 0 to n x into x minus 1. Now expressing mcx in factorials, it is n factorial by x factorial into n minus x factorial p raised to x q raised to n minus x. Here also we can omit the terms x equal to 0 and 1 because in summing when x equal to 0 the entire summation becomes 0. When x equal to 1 it is 1 minus 1. So 0. Therefore nothing happens when x 0 and x 1. Therefore summation is starting from 2 onwards. That is x equal to 2 to n x into x minus 1. Now n factorial by x factorial into n minus x factorial p raised to x q raised to n minus x. Now if you consider the terms of x factorial, you can see that they are from 1, 2, 3, 4, etc. x. So we can see that the last one terms are x and x minus 1. So we can cancel the last one terms in the x and x minus 1 the numerator. So you can do some simplifications also. You can take one n and n minus 1 outside and p square is outside. That is n into n minus 1. Now p square summation x equals 2 to n minus 2 factorial by x minus 2 factorial n minus x factorial p raised to x minus 2 q raised to n minus x. Can verify that terms balanced out now. You can see that this n factorial is now n into n minus 1 into n minus 2 factorial and this p raised to x by taking this p square and p raised to x minus 2. The last q raised to n minus x unchanged and the denominator x minus 2 factorial because of cancelling x and x minus 1 in this x and n minus 1 and the last n minus x factorial without any change. Now you can see that this is equal to n into n minus 1 p square summation x equal to 2 to n. Now all these factorials can be jointly written as n minus 2 c x minus 2 p raised to x minus 2 q raised to n minus 6. Next our plan is to compare this summation with a binomial expansion and show that it is similar to the expansion of q plus p whole raised to n minus 2. That is, we can write it as n into n minus 1 p square in a bracket q plus p whole raised to n minus 2. That means that if you expand q plus p whole raised to n minus 2 using binomial expansion, the terms will be same as sigma x equal to 2 to n minus 2 c x minus 2 p raised to x minus 2 and q raised to n minus x. Therefore, this is now n into n minus 1 p square. Thus, e of x into x minus 1 is n into n minus 1 p square. So, e of x square is n into n minus 1 p square plus np. That np is from the side of e of x. So, e of x square is n into n minus 1 p square plus np. So, variance of x is e of x square minus e of x whole square. So, we substitute the values of both expectations. It becomes n into n minus 1 p square plus np, the side of e of x square, minus e of x whole square, that is n square plus into p square, that is n square p square minus np square plus np minus n square p square. So we can cancel both n square p square. It's only n minus np square plus np. If you take one np outside, it is 1 minus p, that is npq. Thus, the binomial distribution has mean np, e of x square as n into n minus 1 p square plus np, and variance of x is npq. Can see that when mean is np and variance is npq, mean will be always greater than variance. This is because q is always less than or equal to 1. Q is a probability, so its value can be maximum 1. So even though we multiply np with q in variance, variance will be lesser than mean in binomial distribution. That's about the mean and variance of binomial distribution.